All right there, Chem Scholars. Just to cover my bases here because I have a lot going on, I'm going to make a couple of videos about the equilibrium stuff, and they'll be posted so that you can go back to them as you need, or if you're out, or whatever. So let's talk about what equilibrium is all about. To get into that, though, let's review about rate laws for a moment. Okay, so here's a reaction between hydrogen and nitrogen to make ammonia. Write out the theoretical rate law. Well, rate laws always take the form of rate equals a constant we call K times the concentration of reactants. So we should end up with something like this. Rate equals K times concentration of hydrogen cubed times concentration of nitrogen to the first order, right? Good. What about if we looked at the reverse reaction? So what if we're to start with ammonia to make hydrogen and nitrogen? Well, now ammonia is the reactant. Okay, so our rate now becomes rate equals K times concentration of ammonia squared. So why did we do that? Well, we have to understand, notice that I would put double arrows into these reactions, okay? We have to understand that many reactions are reversible. So even though this is a reaction that I'm starting with, hydrogen plus nitrogen makes ammonia, I have to consider that the reverse reaction will happen over time unless I prevent it from happening, okay? And so ammonia will break down to hydrogen and nitrogen, okay? So in a closed container, in a closed system where we're limiting the inflow of new materials and the output of any products, if it all stays in the same system, we're going to see both reactions happen over time. But keep in mind, let's assume this is the reaction we started with. The amount of hydrogen and nitrogen over time are going to decrease. The amount of ammonia over time is going to increase. So that means that this rate is going to decrease over time because the hydrogen and nitrogen are decreasing. And this rate is going to increase. Let me get my stupid little face out of the way. This rate is going to increase because the amount of ammonia is going to increase over time. So at some point, we have to consider that those rates are going to be equal. Okay? So if, because the ammonia started at 0, let me go back to this. If this was our initial reaction, we're starting with hydrogen and nitrogen, we're not starting with ammonia. So this rate starts at 0, this rate starts high. But again, this rate is going to decrease over time. This one's going to increase over time. And so at some point, it seems reasonable that those rates would be equal. Okay? And that's what we're talking about here. At some point, the rate of production of ammonia will be equal to the rate of consumption of ammonia. The rate at which I make it equals the rate at which I break it. Okay? And that means that effectively the reaction has stopped. It does not go to completion, which is something we've kind of assumed up until this point. Okay? Now, technically, on a molecular level, the reaction is still happening. We're still making ammonia, we're still breaking ammonia. But if the molecules are being made at the same time as an equal number of molecules are being broken, well, then effectively there's no change. The reaction has ended. Okay? So if we looked at that from a graphical point of view, we would see that the concentration of the reactants A and B are decreasing, but notice that they level off. They don't go to 0, even though that's what we would expect. We'd expect to use up at least one of the reactants, the limiting reactant, but that doesn't happen. Okay? They level off. And same thing with the product. It levels off. They don't go all the way. So the stoichiometry that we might have predicted based on how much we started with is not what we're going to end with. And that's why the stoichiometry is really about the change, not about the initial amounts, because equilibrium will happen. Okay? So we could see that once this graph leveled off, that's where equilibrium is. So, somewhere I'll say around, here, somewhere around 5-6 seconds, seems the curves seem to both have leveled off, more or less. I mean, you could argue, I guess, even out here at around 7 or 8 seconds, based on the zooming in on the graph there. Yeah, maybe around then. Not going to ask you that kind of question anyway, but we see that it levels off, and that's a prime indication that we have reached equilibrium. So if we're at equilibrium, then what we could say is that the rate of the forward reaction equals the rate of reverse reaction. Now, please don't write this stuff down. This is just me showing you an example right now. So in our example, we were talking about the forward reaction being the hydrogen and the nitrogen as a reactant. In the reverse reaction, it was the ammonia that was the reactant. So we have a constant on both sides. So I'm going to bring the constants to one side. I'm going to bring all the concentrations to the other. And so when I take Kf divided by Kr, well, a constant divided by a constant gives me another constant. And so we would have the ammonia squared over the hydrogen cubed times nitrogen. Well, this constant is called the equilibrium constant. And the equilibrium constant is always concentration of products over concentration of reactants. I could have, in the previous slide, divided the other way and done reactants over products, but products are the goal, so we want to put them up top, okay? So it's really concentration of products over concentration of reactants. Now, it's weird because in the rate law, there are specific units to K, but when we talk about equilibrium constants, we drop off units because it's a ratio of products to reactants. Even though the ratio might not totally cancel out, we assume it does, so we say there's no units on the equilibrium constant. Okay, so those of you that forget units all the time, you're in good shape for this. The equilibrium constant does vary with temperature. We're only going to deal with room temperature, so we're not going to deal with any variation on temperature, although we'll talk a little bit about it at the end, but we're not going to really deal with it. But keep in mind, we derived all this by talking about rate laws. And in rate laws, we said we don't include solids and liquids because they have constant concentrations or densities. So same thing's going to be true here with equilibrium constants. We are not going to include solids and liquids. All right, so let's look at an example, or three. So here's three reactions. We saw these when we talked about rate laws, and now we want to write out the equilibrium expression. Take a moment, pause the video, give it a try, and I'm going to go on. So we're doing products over reactants, but we're leaving off solids and liquids. All right, so this is a solid, so I just put a 1 in there. I'm factoring it out. I'm not subtracting it out. I'm just factoring it out. It becomes part of KEQ if it's a solid or a liquid. Same thing with the iodine. It gets factored out, and so it goes into there. So I could have put another 1 in the denominator, but there's no need to. So we're just left with the hydrogen. So it's 1 over the concentration of hydrogen. In this reaction, we have a liquid over here. So again, I start with a 1. So now, products over reactants, I have hydrogen squared, or second order, if you will, times oxygen. And then finally, in this reaction, we do products over reactants. Now they're all gases, so I'm including it all. So I get carbon dioxide to the 4th, times water vapor to the 6th, divided by ethane to the 2nd, or squared, times oxygen to the 7th. Okay, so those are called equilibrium expressions. That is hugely important for the rest of the year. We're going to talk about equilibrium expressions all the time. You need to write this out all the time. Products over reactants, constantly. All right? So get used to that idea. Now, technically, most combustion reactions are not really reversible. We're not going to worry about that. If I give you a reaction, you can assume that it is reversible. Okay? So that's all that you need to worry about for this. All right, so the next segment's going to be about doing some calculations with this, but I'm going to stop this video here and make a separate one for that.